Is that okay? We'll continue where we stopped last time. Well, we are trying different thinking strategies. They don't work if there are more than 5 people in the room. It worked totally fine if there was less than 5 people in the room. So I think, now this there is a person or people detection that makes this PowerPoint annotation crash. I think that's the latest theory about that. So all of the news, there is a lot of interest, as you might have heard, in higher throughput interconnects. And there is an alliance now between AMD and a photonic provider announcing that they can do 800 gigabit, essentially a chiplet attached to an AMD hyperscale class processor. We'll see a lot of development in that space, I think. What we did last time, we have talked about edge trigger timing, and we have seen that there are no surprises there. There will be additional quirk that we're going to add to it in the next lecture when we talk about variability, how we basically budget for variability. But that is it for now. What was new was the large-based timing, which is a little bit more complicated. But the way how we broke it up was by timing, comparing the amount of logic that is allotted to a particular cycle to the actual cycle in large-based timing, and figured out if we are borrowing or passing some slack. That's the way how we can do this timing analysis from a cycle to a cycle. Again, we need to make sure that we are correctly constraining this for every cycle or for every half cycle, such that we know when this time borrowing is happening. And this is done by the tools automatically if the design is done correctly. And when you read these timing reports, you will actually get the amount of slack that is being passed. It is more complicated, and as some people have figured out, this is a rich source of problems for finals, prelims, and events like those, if you're about to encounter them at some point. Okay, and there is also asynchronous design, and there are a lot of people who are interested in asynchronous design now in a limited scale. Why do we don't do asynchronous design? Would anybody like to tell us why we don't do asynchronous design? Why is asynchronous design out of favor? I mean, it's even better than large-based design with this time borrowing and things like those. But why is it out of favor? Because it's really hard to verify. And it does come with a non-trivial overhead that in theory is less than the flip-flop and clock-based overhead, but in practice, nobody has figured out how to make it really low. But the biggest thing is the verification issue. So let's talk about the large design first, and then we're going to cover flip-flops. And I'll try to ink a little bit, and then if it crashes, we will stop doing that. Okay. So remember, we talked about the design of 2 input muxes. There are 2 ways to build a mux. One is by using C-square MOS gates. The other one by using transmission gates. And we have also asserted that in the end of the previous lecture, that those 2 are basically identical. If I put a line and connect these 2, and those 2 are identical. So the difference between the 2 is just the wire from the stack node on top to the stack node on the bottom. Is there a difference in logical effort between the 2? The one on the left is really easy to apply the method of logical effort to. The one on the right takes a little bit of an extra skill. Let's try to apply optimal sizing to the gate on the left. So to size it optimally in a FinFET process, this would be 1.5, 1.5. This would be also 1.5, 1.5, and it stopped working. So I'm going to switch over to inking will not work. We're switching to iPad from next time if I try inking again. So I actually filled this partially here while we are practicing. But the point here is, if I have a C-square mouse gate and it has a cell input and an A input here, what's the logical effort of this thing? This is sized as, this is my output over there. So if this is size 1.5, 1.5, 1.5, 1.5, what's the logical effort of the input A? So it is 3 divided by the input capacitance of a unit inverter, which is 2, which is 1.5. And if I do this, if I add the second stage here with the input B, this is the cell bar, and this would be what is the logical effort of the input cell? Select input. Well, the input capacitance here is also 3 divided by 2. But I have 2 select inputs. I will need to find out, if there is, generating this additional input select bar creates any additional logical effort. I'll leave this for now as for a second for now. Now, but my other question here is, how do I size the other gate? The transmission-based mux. Or, in other words, what is the logical effort of transmission gate or a transmission gate? In order to answer that question, let's try to figure out how do transmission gates or how do pass transistors behave. So, when I take a look at this, I know that an NMOS passes a strong 0 or 1. 0. Okay, so that means that the resistance or in high to low transition is going to be what we expected, right? And what we typically have in a standard CMOS. In high to low, it has an equivalent resistance of standard inverter, right? So the equivalent resistance here is going to be R. It passes a weak 1. What does that mean? The resistance in low to high is high. How much high? You'll have to simulate it to figure this out, but it's like 2 to 3 times, depending on what kind of threshold and what kind of voltage you're using. Or if it is, operating at a low voltage with a higher threshold, it's much worse than that. But let's say on the average, it's like 2 times worse. That's, the lowish to standard low threshold, and nominal supply. So this is going to be 2R. And the same thing holds for the, when I switch these, so this is HL, LH, HL, LH. So the same holds for PMOS, but in the opposite direction. So when we have a transmission gate with both NMOS and PMOS, essentially we have an action of 2 resistors that are in parallel with each other. The equivalent resistance is R in parallel with 2R, which is about 2/3 of an R. Exactly 2/3 of an R, but because of the my arbitrary assignment of what is LH in NMOS or HL in PMOS resistance, I get about 2/3. So both of these transistors are on, but they don't have the resistance to half. They produce 2/3 of an equivalent resistance. So that is also, of course, assuming that it is sized, the transmission gate is sized as 1, 1. So let's now take a look at what happens, how do we find out what's the logical effort of this thing? So we have an inverter driving essentially a resistor that has resistance of 2/3 of R, and this is Y. And I have an input A. How should this A be sized? And should it be 1/3? It's a good guess. A few more options. This is, remember, this is kind of a fakeish thing that we have done because we ignored, in order to do this. This is essentially a transistor that has, we should still view this as a transistor with 2/3 of a resistance. What is the sizing of that transistor? How should I size? Essentially, I'm looking into sizing something like this. And something over here is 2/3 of an R. What does that mean? What kind of a sizing that corresponds to? 1.5 in a transistor stack. Get my play with sizing over here. Therefore, how should this guy be sized? Also 1.5 in order to get the equivalent resistance of those two to be equal to a single pull-down resistor with a width of 1. The same that we have seen in an NMOS stack. Now, I've approximated quite a bit of stuff here, but this is roughly correct. The catch here is, so what do we get here? So this is my input A. So my input A should be sized 1.5 and 1.5. So what is GA? Well, it's again 3/2 or 1.5. So logical effort of both of those are going to be the same. The logical effort of the select input is going to be a little bit different because remember, I have 2 of those basically wired in parallel, and I have 2 of those acting in parallel. I have a higher load on the select input because each of those is sized as 1.5, 1.5. And those are sized 1 and 1, NMOSs and PMOSs. So select input has a lower logical effort here. Yes?
Sorry, I maybe missed it, but you want to have
that would be, if these things were linearly adding, but remember, these are all velocity saturated transistors. Because of the impact of velocity saturation, it looks exactly the same as my two input NAND. Now you can work back all those equations and try to catch me in my lines, but they're not big. They're small.
Why do we treat this series resistance as part of that inverter as opposed to why don't we treat it like a wire, because the wire also has resistance. Why do we lump it to this inverter?
Yeah, the question here is, why do we lump this transmission gate into the inverter? Because we can't define, the logical effort of a transmission gate is not defined because we don't know the resistance of the thing that is driving it. So only those two things together can have a defined logical effort. It has to be a low resistance path to ground in either case. And we're going to compare what is that resistance of the path to ground to a unit inverter. And this is the only way I can find that out. Otherwise, it's undefined. It becomes, driver dependent, which is something that is important to keep in mind when we look more into flip-flop design and stuff like that. All right. Now, I did walk you over one more thing here. I kind of hid one more thing. I have to generate true and complementary select signals, and you'll find out I'll need to generate true and complementary clocks. What's the logical effort of an inverter fork, which is this? So these two things are driving exactly the same capacitive load, CL, and there is some kind of a C in here. And that C in can be broken down to, let's say, Cx and C in minus Cx. How should this thing be sized such that the delays of the top part are the same as the delay in the bottom part? Anybody has any suggestions? No. Because we need to basically create a true and complementary signals here. So this is my CN. This is some clock. And this will be CK and CK bar. Is it?
The load is being divided.
Yeah, exactly. So I have some intrinsic delay and some fan-out induced delay. So first, to size this optimally, what should be the capacitance here? Or should this guy be sized? Yeah, so this would be CL over CX. Is that good? Square root? Do you agree with that? You guys are giving me some scary stares here. So what is the delay of the top part? Well, it is 2 square roots of CL over CX plus 2. And that has to be equal to, what's the delay on the bottom part? Yeah, CL over Cin minus Cx plus 1. Right? If my CL and Cn are given, I can solve this for Cx. I'm not going to put myself through solving a quadratic equation, but if you find out, if you solve that, you'll find out that G of the fork, and this thing is called the fork, inverted fork, if sized correctly, is approximately 1. So from the clock input to generating complementary clocks, the added logical effort is very small. I mean, it will turn out to be somewhere between 1 and 1.1. Believe me, you can go ahead and solve that. So it simply tells me that my select input, I can calculate the input capacitance is like simply summing through and complementary ones, which is what I'm going to do going forward. Now, we have talked about latches and flip-flops, and we would like to step back and analyze how do they work and what do they do. We have talked about this concept of a flip-flop and its clock to output delay versus setup time versus hold time. And in general, when you talk to these timing experts or people who really analyze, do high performance timing and design of high performance flip-flops and latches, they'll tell you two things. One, that the flip-flop is a hard barrier, hard timing barrier. Latch is a soft timing barrier. That simply is, in other words, what I described last time. You can borrow timing across the latch boundary, but you cannot borrow time across the flip-flop boundary. And this picture is trying to illustrate that. So this picture here is trying to illustrate the dependence of PB to Q on PB to C. Depending on when does the data signal arrive with respect to the clock, what is the overhead of having a flip-flop in our system versus what is the overhead of having a latch? So a lot of information in one graph. Try to digest this in one slide. So the minimum penalty on time is the time that it takes me, if that data arrives just on time, right together with the clock edge, what is the overhead of having a flip-flop in the system? So that is essentially the clock to Q delay. But if data arrives earlier, it does not get any reward for arriving early to a flip-flop. It basically consumes all of the slack on the flip-flop. So there is an added penalty when you just linearly add any separation between data and the clock and add that to the penalty of having that time. In case of a latch is conceptually soft, which means that if we are arriving at a hard edge over here, if we have to relaunch the data, our penalty is what? The Q delay plus any added time we have over it. But if data arrives into a transparent latch, and say it's a transparent high latch, the clock is high, the data goes through it after clock, after the Q delay. So this is what it's trying to do. This is what is the graph trying to illustrate. If we are arriving to a non-transparent latch, we have, we are adding linearly P2 to our latch overhead. And if you're arriving to a transparent latch, then there is no overhead of that. And then finally, if it has to be relaunched, I mean, this essentially corresponds to a failure of missing the setup time on the launch or missing the setup time. The concept of this that we'll see a little bit later in the next lecture one more time is I don't have to, when using launches, I don't have to account for impact of a jitter or the skew if the data is arriving over here. This, these three graphs are showing that this is kind of, the whole thing is moving with respect to the plot and skew or even B2C in the area. So if data arrives during this flat plot, we don't care about skew or the jitter as long as we don't hit one. So that's one of the big advantages of watches. And that's why people tend to use them really places where they do release transits. In this picture, should be noted that this flip-flop is drawn as really a sharp angle down here. In practice, all flip-flops have a little bit of a variety. If you're designing your class project or your master's piece, class chip takeoff, you're not counting that. But believe me, people who design very high performance designs do care about that feature. And we'll see a little bit of that going forward. So let's try to find out how these latches look like, and how do we analyze them? How do we find their output delays and setup times? I mean, all times are going to be automatic. In general, the way how we design them is by combining some transmission gate structures and some C-square MOS structures. The way how it is shown here, in the past, people used to design this without this feedback converter. If you don't have a feedback converter, this node would have been dynamic. And that's not good. That was allowed about 20 years ago, but became banned because we don't want to have in digital systems, we don't have to worry about dynamic gates. So that node is nowadays staticized by having an inverter in the feedback. What's the problem of having an inverter here in the feedback? Yeah, I mean, something, how is the new value being written in here? Say, if this is a holding A0, that means that this inverter, there is an NMOS transistor down here that is on, that is holding this down, and this guy would like to write A1, so another path that has at least two devices in a stack. In order for this to work across all process corners in a range of supply voltages, this has to be a lot bigger than that inverter. That is really hard to guarantee across a range of supply voltages. So what do people do? Yeah, they break this loop and put another one. So if this is CLK bar, this will be working in the opposite phase, CLK bar, CLK. It's like a multiplexer. Yeah, we have either, to that node, we either multiply the new value or the old value. The other way how you can look at that is either B or Q are being multiplexed. The same thing holds for a C square mass. We can put this direct feedback, or what they call it, a jam latch. But people rarely do that. Instead, they will break the feedback. And now you will find out that you have all 4 possible combinations. C square mass in the input, C square mass in the feedback. Transmission gate in the input, C square mass in the feedback. C square mass in the input, transmission gate in the feedback, and transmission gate and transmission gate. Really depending on how to balance these loads. If you open up the standard cell libraries, you'll find all kinds of things there, and there is an layout that plays some factors in there, and a few other things that I'm gonna address in a little bit. The way how these latches look like, essentially we will have, as we mentioned, we would have 2 types of latches: transparent high and transparent low. This is an example of a transparent high. This is a transparent low. And by the way, in the past, it used to be popular, it used to be possible to have no inverter, no driver that is a latch. That is not possible anymore. That is not allowed anymore. What is the problem associated with having no inverters at the input D? This is taken from a book that was published in 2001. Yes. It is bidirectional. That is correct. But more related to what Ken asked me a little bit ago. I don't know what is the logical effort of this gate. It depends on who is driving, or which gate is driving this. So that means that P to Q delay and the setup time are going to depend on what is driving. In order to do that, by the way, this was done up to like, this is something if you can look through the literature, and their Mac G5 was the last one of the OS processor that was the last one. There is a heavy burden on the timing analysis of whoever is doing this, physical design timing analysis, that essentially they would have to figure out, in order to do the timing, they need to figure out which gate is driving it and how far away is it. And if you're doing something up to G5 class of it was I think G4, Mac G4 it was possible. I mean, you have a big design team and happen to it for a simple core processor that we could get over there. But then things became so complicated. It was not possible. I mean, we would have needed design teams that are way bigger than companies can afford. So that path has been abandoned, and all the latches now have a driver in front. A few things. Quizzes today. It is in lecture, and it is in 25 minutes. There is a lab that is due this week, and you have lab midterm reports due next week. Midterm reports are 4 pages, simply a conference format. Title, abstract, and a content for 4 pages. How do you write an abstract for a paper? I write this down, it's very useful. Should have 5 sentences. If you adhere to this rule, people will appreciate it whenever you end up writing content. What should be the first sentence of your abstract? Even if you write a technical report in the content, decide to publish papers. Even if you write a technical report and you write a summary, what should there? Yeah, what is this about? define the problem that you're solving. What should be in the second sentence? What's the limitation of the state of the art? Now, carefully crafted there, so it's just that you're not trashing someone else, somebody else gets offended over that sentence. But you basically say previous solutions have this kind of limitation. There's this problem, but there's here the shortcoming. What is the third sentence? What you have done to solve the problem and overcome that limitation that you've identified in the sentence. What goes in the fourth sentence? Logical. What goes in the fourth sentence? What goes in the fourth sentence? It's also good they go in the fifth sentence, before the fourth sentence. How did you get those results? Yeah, you write that in the fourth sentence. What is your method? Have you designed the chip, or have you just simulated? Or have you done some kind of comparison? Right? So it's a natural flow of 5 things. Subject matter, what is the problem? What limitation is the state of the art? What is your solution? How do you get the result? What is the result? Sometimes you'll find when you read these papers and you will be asked to review, as you're now, pretty much everybody's a grad student, you're being asked to review other people's papers. They write you a really convoluted abstract. You can't figure out what they did. There's another rule when you write these papers. You should be able to go from the abstract and skip the middle, go to the conclusion. It should make sense. Should make even more sense to read the abstract, to read the introduction and go to the conclusion, and the whole thing should make sense. And you'll find out, I've caught myself many times. That's how I read papers, how I review them. I read the title. If the title makes sense, if it is interesting, it's very enticing to read the paper. I try to avoid the bias of me judging the paper by the author's names, but many people will do for the affiliation. That works in your favor, so title abstract invites you to read more, and you jump to a conclusion, it makes sense. Then read it in that way. So the purpose of your paper is to try to invite people to write the whole thing. Write a good abstract, write a good conclusion, write a good introduction, and then middle part. Just this for one. Another important thing in these midterm reports is to make sure that since you're just doing literature study, you have to have a setup for your experiment, proposed experimental setup, how you're going to verify what you've done. So your final report is more going to be like what I've just said. Your intermediate report will have a proposed study in it. Okay. Let's do this super quick. Yes.
So for this report, you folks just need to sign the proposals.
You don't need to have any results now. So this, what should be in this report? Should be a problem statement. Should be this lengthy explanation. Your text would basically match that second sentence that you should show us that you understand what is the state of the art in the subject that you picked. Majority, 2 pages should basically dive into the previous existing solutions to the problem that you've identified. So identify the problem, and then talk about how people have solved it. Make some hypothesis from that. That either this is the best method, the method A is the best of all of them, and then design your experiment to prove that hypothesis. Or in rare cases, it may happen that you will say that none of these methods make sense, and you're going to come up with a better one. If you do it really well, I mean, can just continue and wrap it up as a dissertation. In most cases, this is just a learning process, and you'll find out that existing solutions may be still good. But we have had class projects where somebody actually managed to get that crack in and come up with something that is better than the state of the art. But in order to do that, you need to understand what is the state of the art. So the point of the midterm report is to read those papers, identify what's the state of the art, and write about it. Okay. Very quickly through here, illustration of setup and hold times, because we'll need them to calculate the actual setup and hold times. We did this in 151, in case you've forgotten. Here is what we're going to try to do. We're going to try to plot the delay for a transmission gate latch as a function of data to clock separation. I could have plotted it like the previous slide, what I had. I could have been plotting clock or data to Q delay, and then I would have gotten something that drops down, gets flat, and goes up. But for now, let's just take a look at P plot to Q as a function of P decreasing. All right. So when data arrives into a transparent latch, this thing, it does not affect any of the waveforms we have over here. And essentially, my P plot to Q, it arrives into a closed latch. If it arrives anywhere in there, it does not affect the propagation delay. As data gets closer and closer and closer, I start violating the setup time, and my clock the delay increases. Eventually, the latch will fail. We've seen that before. The same story holds for when we are evaluating the whole time. As the data arrives closer and closer, we typically will have negative hold times, and it is going to run into a latch. The way how we define setup and hold times essentially is by looking at the increase in the plotted Q delays by 5 or 10%, depending whose library you're looking at. Let's for now take 5%. Although if you take a look at TSMC's libraries nowadays, they're 10%. Setup time is defined with respect to 10%. And the same applies to both setup times and hold times. All right. So I need some space in order to do this. We can do this with using one method of logical effort. Believe it or not, it takes a little bit of good understanding of the logical effort. But they should be able to fit the whole thing right here. All right. Let's take a transmission gate latch. And it's going to be the same thing, whether I take a transmission gate latch or I can take, I don't know, I can do this one. C-square loss. All right. What is a delay of testing by using methodological effort? I'll say that my overall fan out is 1 for now. That is suboptimal. Why? But I'll do it now for the ease of calculation, so I don't have to do square roots. Why flip-flops should not have a fan out of 1? What's the optimal fan out for an inverter? 4. What's an optimal fan out for like an AND gate? More or less than 4? It's a little less, like 3-ish. What's an optimal fan out for 2 inverters or a pair of inverters? More than 4 or less than 4? Not quite 16. Oh yeah, it's somewhere around, close to 16, but something like that. So if I have 2-stage network, this should drive some kind of a fan out for optimality. Otherwise, you throw a latch in there, your timing optimization, your synthesis tool is going to throw a buffer after it always. You try to optimize that. So, but for now, let's assume that the fan out is 1. So in order to find what is the delay here, what should I do? I should find out what is my GF. What is GF here? So this gate has a logical effect of 1 times F1, so this is G1 F1 times G2 F2. Okay. What is this? What is the value? Just tell me right away. F is 1. F1 times F2 is equal to 1. What is G1 times G2? I just found what was G1. We know that G2 is 1. So this whole thing is you agree with me? All right. So what is GF? Well, GF. Well, that is equal to the square root of GF, and that is about 1.2. That's it, give or take. So GF of this stage should be 1.2. GF of this stage should be 1 over 1.2. What's the capacitance here? Well, it's less than what is the output capacitance. So it's kind of weird. You see that, the weirdness of choosing F that is 1, the overall F that is 1, but that's the price that we, you can repeat this calculation for an optimal fan out, of course. So what's the propagation delay? Well, it is right GF1 plus P1 plus GF2 plus P2. Can we evaluate this? So I know that GF1 is, and this whole thing will be multiplied by some P unit. So this will be 1.2. What is P1? What's the intrinsic delay of C square mass? Well, I have 1.5 and 1.5 all load over here, so it should be what? It's divided by what is the unit inverters P1, so it's 1.5 plus 1.2 plus 1, right? P unit. So this whole thing is equal to 4.9. What is that? approximately. It's about 5 unit delays. I mean, these numbers will work out. So that is equal to 1 10 out of 4 inverter delay. And that is something that is, you'll find out that this agrees. So propagation delay, in this case, it is both P clock to Q and TB to Q. In this kind of a logical effort approximation, both of them are about 1 10 out of 4 inverter delays. There is a difference. Why does the clock to output delay differ from clock data to output delay? Can anybody tell me quickly which one of them is going to be longer, which one of them are going to be shorter? Exactly. So there will be some intermediate node that will need to be discharged. Which one has to do that? Or if you look at this, the one that arrives the last is the faster one, so that clock to output delay would be the faster one. Okay, now I figured that out. Can I use that to calculate my setup and hold times? How would I? Yes. If I do what? You put it over there. Yeah, this would. We'll talk about setup time in a second. Essentially, you are prioritizing which input matters here. Usually, people will put clock as the last arriving signal next to the out. We'll take a look at the setup time in a second. But what happens when we have at a point when we are trying to calculate the setup time? What is happening here? My data is arriving so late that this node is not reaching its final value. So if you look at a latch, there are two components of a delay. The first part, that is a C-square mouse, and the second part, that is the inverter. Because of the setup time violation, which one of those two gets extended? Which of the two gets extended? A lot of them, this inverter. So this inverter's delay is extended in a way that the overall propagation delay of the latch is 5% longer. Well, if you look at that, that delay is like roughly split in half. You can do the actual calculation, which is telling me that the clock to output, that the propagation of this inverter should become 1.1, 10% longer, or a little bit more than 10% longer. How does that happen? Well, if this input does not reach the rail, does not reach all the way to ground. So by how much of a loss of of the supply of the input voltage does that cause? How much of a input swing loss causes 10% delay push out? Remember, ion is linearly proportional to VDD. Delay is roughly linearly proportional to VDD, give or take around the VDD. So it's about 10%. So we need to find out how long does it take for this input to propagate to to 90% all around. And so I knew that my propagation delay here was this was about 2.7 T unit. This was 2.2 T unit. This 2.2 T unit is going to become about 2.42 T unit, 10% longer. Can you figure out how long, where should the data be to cause that delay increase? I'll leave that to you as a homework. I'll go very quickly over it in the beginning of the next lecture. I'll give a few questions for any questions that you may have. Yes.
Why do you make 10% increase for the perspective? Because like if you want to see the 10% increase in the overall, so you need
5% increase in the overall.
Okay, thank you.
So it's roughly 10%, a little bit more than 10%. That's good observation. Okay, so we have a quiz now. If you whip up the grade scope and go to quiz 1, it will be live in 25 seconds. Eric has set it, or Eric and I have set it up live. It's fairly, has a lot of questions. Some of them are just simple clicks. So go quickly for those. It is closed notes. You don't have time to look at the notes.